Hello there, Mr. Sutton here, bringing you this AB Calculus 2-6 lesson on continuity. We have several objectives in this one. We will be finding intervals of continuity, identifying different types of discontinuities for functions, proving continuity at a specific point, especially with piecewise functions, and creating continuous piecewise functions by finding missing constants. So in order to promote some continuity between where we've been and where we're going in terms of material, using interval notation, we're going to write the domain, intervals where the limit exists, and intervals of continuity for the function in this graph right here. Just a few definitions before we start doing that. With domain, remember, we're talking about where the function actually exists. So that would be anywhere your function has either solid dots or solid lines. For where the limit exists, we're talking about the left and the right-sided approaching the same constant. And for continuity, well, we're talking about places where the function has no discontinuities, which is to say we don't want any holes or breaks in the graph. So general strategy for doing this, figure out the trouble spots and then leave those out, and just write the intervals around those. So pause the video and write out those intervals. All right, so for domain, we're just figuring out where we do not have a solid dot or line and leaving those out of the graph. So our graph starts at x equals -4. We're going to put a bracket there to show that we're exactly equal at -4. And then that goes until we get to this vertical asymptote where the function is undefined at -2. And I'll use the parentheses there because I don't want to actually say -2 is part of my domain. Now to link this up with other intervals, we use this little union symbol here. And then my next interval is going from -2 all the way until, well, +2. We don't have to worry about this jump in here because we have a solid dot to replace this open dot, but here at 2 we have an open dot and nothing else. And then we're going from +2 all the way to where? Well, infinity, because we just keep going. All right, let's check out the limit now. So this is going to be all the spots where we're approaching the same place from the left and the right. So we can start again at -4, and then we are kind of approaching the same infinity at this asymptote, but infinity is not a constant, so that doesn't count. So we say that our limit breaks down at -2. And then we're going from -2 until we get to this jump, because we're approaching different places at x equals 0 from the left and the right. And then we're going from 0 to where? Well, we don't break our limit at this open dot right here because we are approaching the same place from the left and the right there. So we're just going to keep going to infinity with the limit. Now for discontinuities, we just leave out all the places where we have any kind of hole or break in the graph. So we're still starting at -4, going until the asymptote at -2. Then we're going from -2 to this jump right here at 0. And then from 0 to the hole at 2. And then from 2 to infinity for that. As you could see on that last example, when we were talking about continuity, we had to talk a lot about discontinuities. So it's nice if we have a nice way of actually naming them. In fact, we do. This type of situation here, where you're jumping from one spot to another where these limits don't match up, this is actually called a jump discontinuity. Another example right here, where you have this hole essentially in the graph, whether or not we have a solid dot or not to replace it, this is called a removable discontinuity. You might have also known it as a hole back when you were doing rational functions. And another throwback from rational functions, you might remember asymptotes here. Well, the fancy way of describing those is infinite discontinuities because our limit is going to infinity as we approach them. And one more example that you might not have thought of as a discontinuity, this situation right here where you have a whole part of the graph that's undefined, this is just called an undefined area. Now that we've talked about some of the types of discontinuities out there, we're going to talk about some of the types of functions that have discontinuities, function families. So I classify these into 3 categories. We've got functions that are known to be continuous. We've got functions that have domain-based discontinuities. They're discontinuous because they don't exist at certain spots. And then there are functions that they might exist everywhere, but the limits don't match up, so we get discontinuities out of those. Pause the video and see if you can figure out some function families that go into each of these categories. All right, let's start with this first category. Now, by functions that are known to be continuous, I'm basically saying here that just identifying the function itself is enough to prove that it's continuous. So if you spot one of these functions and you just say it's this type of a function, you've already shown that you're continuous and don't have to do any other proof. So polynomials are the big case here. Those are known to be continuous everywhere. Also exponentials, because you can plug anything in for an exponent. In terms of trig functions, sine and cosine we know don't have any breaks or holes. And another one that people often forget about is the cube root function, or any odd root. Can be defined at any negative, zero, or positive value. Now down here, domain-based discontinuities, a big one is the rational functions, because we're not allowed to divide by zero. And rational functions, those are also going to include tangent, secant, cosecant, and cotan, because with these functions, you could be dividing by zero if sine or cosine has a value of zero. So in general, these types of functions, you're going to get holes and asymptotes possible for discontinuities. Another class with discontinuities based on domain is radical functions, the square root function specifically, and any even root, because we're not allowed to square root negative numbers. So we're going to get an undefined area wherever we have negative numbers being plugged in. And then the last big case is the logarithmic functions. This has a couple. We're not allowed to take the log of 0. That's going to give you actually a vertical asymptote. And you're also not allowed to take the log of a negative number. That whole area with negative numbers is actually an undefined area. So two different kinds of things going on. Last but not least, we have the limit-based discontinuities. So the big case here is piecewise functions, where you could have either jumps or holes at those border values. Now that we've had a little bit of a background on what kind of discontinuities there are and what function families they go with, pause the video and see if you can identify all the places where this function has discontinuities. All right, so when I see a function, I immediately start thinking, where is this thing going to have some problems? This radical stuff up here, I remember I'm not allowed to take the square root of negative numbers. So there's probably going to be some undefined areas because of this radical term up here. Now in the denominator down here, I've got some x's, which means I run the risk of dividing by 0. So I might run the risk for some holes and asymptotes because of my denominator. Let me go ahead now and analyze what areas specifically I'm going to be missing. So up here, if x plus 2 has to be positive, that means that x plus 2, if it's negative, is going to give me some undefined areas. So I'm going to have undefined areas wherever x plus 2 is less than 0. Subtracting 2, that means that I'm going to be undefined where x is less than negative 2. Now in the denominator, to figure out if I've got holes and asymptotes, I'm going to go ahead and factor what I've got here, because that'll help me figure out what's going to zero out that denominator. I can take an x out of these, so that's x parentheses x minus 6. And just in general, the holes that you get are going to be removable discontinuities. Vertical asymptotes, you might remember, those are going to be your infinite discontinuities. So because I can cancel out these x's, that means I have a hole at x equals 0, and that means that I have a removable discontinuity at x equals 0. Since I can't cancel out this x minus 6, that means I have an asymptote, which is to say an infinite discontinuity at x equals 6. So at this point in the lesson, we have hopefully an intuitive understanding of continuity, and even also how to find out discontinuities in some functions. But how can we prove that a function is continuous at a specific x value? For that, we need an official definition of continuity. So to get to that definition, I've got 4 graphs for you. For each graph, pause the video and say whether you think the function is continuous at x equals c, and also give a mathematical reason for it, something involving f of c and the limit as x approaches c. Pause the video, give it a try. All right, so for this first one, eyeballing this is definitely not continuous. And the reason it's not continuous is that the function simply does not exist at x equals c. F of c is dne. For this next one, f of c does exist. We have a solid dot there, but I think we can still say this is not continuous. We have this break in the graph, this jump. And the reason behind that is that we're having a different limit as you approach from the left and the right. We're not going to the same place. So we could say that the limit as x approaches c does not exist. For this next one, the limit definitely does exist. We're approaching the same place. And also f of c exists. But we can still say this is not continuous. This is another removable discontinuity, just like our first graph had. The problem here is that the limit where we're going and the function value where we end up do not match up. f of c and limit as x approaches c of f of x don't equal each other. This last graph, I guess fourth time's the charm, this is definitely continuous. We just know this by looking at it. And at this point, we're going to look at what this graph has that these other three don't to get our official definition of continuity. So we can say f of x is continuous at x equals c if the following conditions are met. So this first graph had the problem where f of c did not exist. So f of c has to exist. This next graph had the issue where the limit didn't exist. Well, the limit at x equals c has to also exist, which means specifically, and you have to show this, that the left side limit and the right side limit actually equal each other. For this last one, we had the problem the limit and the function value didn't match. Well, they need to. Limit as x approaches c of f of x and f of c have to equal each other. So if we have all three of these conditions, we can prove we are continuous at a point. Now that we've got our definition of continuity, let's use it to figure out whether this piecewise function is continuous at x equals 0. So in practice, to show that our function value and limit exist and they match up, we need to start by figuring out the left limit, the right limit, and the function value at the x value in question. So pause the video and take a moment to figure out all three things at x equals 0. All right, so let's start with the left-sided limit at 0. That's going to be what I get by just plugging 0 into x minus 3. That's going to give me a value of negative 3. The right-sided limit at 0 is going to be what I get by plugging 0 into this second rule here. That's going to be also negative 3 because everything else zeroes out. And finally, my function value at 0, I'm going to just use the rule that has the equals in the condition here. So that would be the first rule. 0 minus 3 again gives me negative 3. Now, by showing that f of 0 equals negative 3, I've already shown that my function value exists at 0. So that was the first condition already. But these three things by themselves aren't enough to show the next two conditions. So to show that my limit actually exists at 0 and that the limit matches the function value, I have to, if all three of these things exist and they match, I have to explicitly show that the two-sided limit equals the function value. And only then I can say the function is continuous at c. So I need to explicitly write out that the limit, the two-sided limit as x approaches 0, equals f of 0, like so. By writing out that these two things match, I've met my third condition, and by saying that the two-sided limit equals a constant, because that's what f of 0 is here, I've met that second condition about the limit existing. So I need all of this to prove all three conditions. Once I've done that, I can say that we're continuous at x equals 0. So this is what we do if all these three things match. If something does not match or doesn't exist for one of these three things, just state the problem and then that the function is not continuous at x equals c. Here's another example for you to try out. Figure out whether this function is continuous at x equals 1. All right, so again, we're going to try out the left, right, and function value here. Left-sided limit of f of x as x approaches 1 from the left. Again, we're using this first rule, so that's going to be 1 plus 2 over 1, so that's 3. And now the right-sided limit, we'll be using the second rule here. 1 squared plus 3 gives us 4. And before we even bother finding the function value, we already see that these limits don't match up. So we can immediately say that since the left-sided limit and right-sided limit don't match, the limit in general does not exist. So we are not continuous at x equals 1. And just in general, what this means in terms of discontinuities, if you had to identify what's happening here, if we're not going to the same place from the left and the right, if our limits don't match, that means we're going to have a jump discontinuity there. We'll do one more example. Pause the video and figure out whether this function is continuous at x equals 2. All right, so left-sided limit, we're going to be using this first rule for x less than 2. So 3 minus 2 gives us 1. And now let's just do the right-sided limit. That uses this last rule where x is a little bit more than 2. So that's going to be 2 divided by 2, which also gives us 1. So our limits match, so that means our limit exists, unlike the last example. Now we have to find the function value at 2. That's going to use the rule where x equals 2, this rule here, and that has a value of exactly 2. It's just a constant function. So we see here that the two-sided limit as x approaches 2 and f of 2, they both exist, but they don't match up. They are not equal to each other. So therefore, since we violate that third condition of continuity, we can say that we are not continuous at x equals 2. Now, what kind of discontinuity is this if the function value and the limit don't match up, but both exist? This is going to be a removable discontinuity if we have a limit that does not match the function value. To start things off, we're going to review continuity a little bit and use it in a different way than we have been. So let's say you've been charged with making a highway that has no brakes in it. We want to find the values of a and b in this highway function here that make this function continuous. Maybe there's some futuristic highway maker that you can plug functions into. So how do we do this? Well, just to get a visual of what's going on, I made a little Desmos slider here just to see what we're up against. So we have these three different highway pieces, and we're trying to change the a and b values so these things actually match up. But we need to do it algebraically because we can't just see one of these problems and plug it in Desmos and solve it every time like that. So we're going to do A together, and then you'll try B on your own. So to do one of these, we're going to start by finding the left and the right limits and the function value at the border values, because that's really where we have this risk of these jumps that we're trying to make not so jumpy. So left side limit as x approaches 2, that's going to be a times 2 squared, which comes out to 4a. And now we also need to find the right side limit as x approaches 2, which also happens to be the function value at 2. So I'm going to write limit as x approaches 2 from the right equals h of 2, and that's going to be 2 cubed, which we know is 8. And at this point, we're just going to force these things to be equal. So set the values equal to each other, set the expression equal to each other, and solve for the missing letter. So we've got 4a equals 8, so then a equals 2. And let's just go back to Desmos and see if a equals 2 actually works. So let's move my slider to 2, and we see that, yes, these things are linking up the way they should. Oh, by the way, you do need to include this h of 2 business in here, because if you're trying to show people that you found things that make this function continuous, well, you have to prove continuity one way or another, and that involves the function value. All right, pause the video and see if you can find the b value. All right, so for the b value, we need the left side limit as x approaches 4 now. We're using the second border value, and that's also going to be h of 4 because we've got the equals there. So that means that h of 4 and the left side limit of 4, we're going to be doing 4 cubed. And we know that 4 cubed is 64. Now we need to find the limit as we're approaching 4 from the right side. Now, if you try doing that right away, you'll see that you get 0 over 0, which is no good. But we can actually cancel out these x minus 4s. And if we cancel those out, we see that our right side limit is just going to be 2b. So setting 2b and 64 equal, we see that dividing by 2 gives us a b value of 32. And going back to Desmos, let's see if 32 works for the b value. So moving that up, when it links up, we indeed have a value of 32. There we go. So that's it for this one. Thanks for paying attention continuously. Until next time, Mr. Sutton signing off.